This tape, the third in our series on trigonometry, deals with some more trig identities. We will be continuing the development of relationships and identities involving the trig functions that we started in the last video tape. Okay, I'd like you to recall for a moment the definitions of trig functions that I gave you in trig tape number 2. Okay, we take an angle A in standard position, that is one whose vertex is at the origin and whose initial side runs along the positive x-axis. We pick a point P, any point on its terminal side. Let's say we pick the point with coordinates x, y. R represents the distance between this point P and the origin. All of this is true. We define the following 6 trig functions for the angle A. Sine of A is y over r. Cosine of A is x over r. Tangent of A is y over x. Cosecant of A is r over y. Secant of A is r over x. Cotangent of A is x over y. In those cases where it's necessary, I've specified, of course, that we never divide by 0 in our mathematics, so since x or y could possibly be 0, these definitions are only valid. Okay, for example, tangent of A is y over x. It's only valid when x is not 0. Okay, in the last video tape, we developed the quotient relations and the reciprocal relations. The reciprocal relations, that cosecant of A is 1 over sine A. Secant of A is 1 over cosine of A. Cotangent of A is 1 over tangent A. And the quotient relations, that tan A can be found by taking sine A and dividing it by cosine A. And that cotangent of A can be found by taking cosine of A and dividing by sine A. Okay, all of this was in trig tape number 2. We'd like to continue to develop trig relationships. The ones we're going to develop now are called the Pythagorean identities. Okay, let us start by making use of the fact that if r is the distance between the origin and point P, we can write r as the square root of x minus 0 squared plus y minus 0 squared by using the distance formula. We have a formula for the distance between 2 points, which we learned in our algebra classes. The distance between 2 points is the square root of x2 minus x1 squared plus y2 minus y1 squared, where the 2 points are x1, y1, and x2, y2. And what we have here are 2 points, one of which is 0, 0, that's the origin. The other one is x, y. So we have the square root of x minus 0 squared plus y minus 0 squared. Or that r is equal to the square root of x squared plus y squared. Squaring both sides of this equation, we get that r squared is x squared plus y squared. Okay, now the reason the identities that we will derive from this equation are called Pythagorean identities is, well, one way is to say, well, the distance formula is proved using the Pythagorean theorem. Another way is to say, if our angle A had been in the first quadrant, okay, so that we had a situation like this, angle A is in the first quadrant, and this is, say, a point P with coordinates x, y, and r represents the distance between the origin and point P. If we were to drop a perpendicular from point P to the x-axis, we would form a right triangle, the legs of which would have lengths x and y. If point P is x, y, okay, that means it's x over y up. This leg must have length x and this length y. The hypotenuse is r. And we see that this relationship x squared plus y squared equals r squared is just the Pythagorean theorem for this right triangle. In a right triangle, the sum of the squares of the 2 legs is equal to the square of the hypotenuse. X squared plus y squared equals r squared. Okay, so relationships developed from this starting point are known as Pythagorean relationships. Okay, let's start with the x squared plus y squared equals r squared. and see what relationships we can develop. Okay, to begin with, we can divide both sides of this equation by r squared. If we were to divide by r squared, that means dividing both sides of the equation and dividing each and every term by r squared, we would get x squared over r squared plus y squared over r squared equals r squared over r squared. We can rewrite this, instead of x squared over r squared, as x over r quantity squared plus y over r quantity squared equals r squared over r squared, which of course is 1. Now going back over here, we see that x over r, going back to our definitions, notice that x over r is cosine of a and y over r is sine of a. Okay, bearing that in mind, let's go back here. X over r, that's cosine of a squared plus sine of a squared, y over r squared, equals 1. This is a very important identity in trigonometry. It is probably one of the most often used identities. Cosine of a squared plus sine of a squared is equal to 1. Very often, however, we write it in a slightly different form. There is a shorthand way of indicating the cosine of an angle quantity squared. Okay, you see, here you need parentheses. If you didn't have parentheses and you wrote cosine of a squared, it would not be clear whether you meant the cosine of a squared or cosine of a quantity squared. To eliminate that confusion, if we want to indicate cosine of a quantity squared, what we do is we put the power right after the name of the trig function. So we have cosine and then a power of 2 and then a. Cos squared a plus sine squared a equals 1. Where cos squared a means cosine of a quantity squared. In general, we use this shorthand to indicate powers of functions. Okay, in the following way. If we want to write sine of a to the nth power, we can write sine, then the power n, then a. Here we do not need any parentheses. This is true if n is not equal to minus 1. Okay? Sine of a quantity cubed is sine cubed a. The only time we don't use it is if n is equal to minus 1. If we want sine of a to the minus 1 power, or 1 over sine a, we don't put the minus 1 up here. This sign with a minus 1 up there has a special use in our calculus classes later on. We don't want to confuse it. Okay? So aside from minus 1, all other powers can be indicated by this shorthand. So we have cos squared a plus sine squared a equals 1, the first of our Pythagorean identities. Now this came from starting with x squared plus y squared equals r squared and dividing through by r squared. We can also take this Pythagorean theorem and divide through by x squared, or divide through by y squared, and we'll get two other Pythagorean relationships. Let me put them down for you over here. Let's say we started with x squared plus y squared equals r squared. And this time we divide by x squared. So we get x squared over x squared plus y squared over x squared equals r squared over x squared. Or 1 plus y over x squared equals r over x squared. Recalling our definitions of the trig functions, y over x is simply tan A. So we have tangent of A squared equals r over x, which is secant of A. So we have that 1 plus tangent of A quantity squared is equal to secant of A quantity squared, or in our new shorthand notation, 1 plus tan squared A equals secant squared A. This is the second of our Pythagorean identities. 1 plus tan squared A equals secant squared A. And finally, by going through this formula that we have over here and dividing through this time by y squared, we will get a third Pythagorean identity. Let's try that. This time we're going to do the same thing. We're going to be dividing through, however, by y squared. X squared over y squared plus y squared over y squared equals r squared over y squared. Or x over y quantity squared plus 1 equals r over y quantity squared. Now, x over y is cotangent of A. So we have cotangent of A quantity squared plus 1 equals r over y, which is cosecant of A quantity squared. Or cotan squared A plus 1 is cosecant squared A. So we have 3 of these Pythagorean identities. All right. I would now like to consider the relationships between the angle A and the angle minus A. In the first videotape on trigonometry, we discussed that a positive angle is one that is generated by a counterclockwise rotation, and a negative angle is one that is generated by a clockwise rotation. The angles A and minus A might look something like this. We have, let's say A is in the first quadrant. We have an angle A, a positive angle generated by a counterclockwise rotation. The angle minus A, okay, would be basically the same size, but generated by a clockwise rotation. Let's pick a point P on the terminal side of angle A. Its coordinates are, say, x comma y. Its distance from the origin is r. Okay. If we were to drop a perpendicular from point P until we hit the terminal side of the angle minus A, right, we would get a point, let's say, P prime, whose coordinates would be x comma minus y. Okay. If this is x over and y up, this must be x over and y down. Since these angles basically have the same size, they're just being generated by opposite rotations. Furthermore, one could show, well, you could show very easily that these 2 triangles are congruent. That's how you would go about working this. Okay, these 2 triangles are exactly the same size and the same shape. Okay. Now, to develop relationships between angle A and of the angle minus A, we will go refer to our definitions of the trig functions. Okay, let us look at the sine of minus A and the sine of angle A, and see if we can see some relationship between them. the sine of minus a and the sine of a. The sine of an angle, remember, going back to our definition here, the sine of an angle is the y-coordinate of the point on the terminal side divided by the distance of that point from the origin, the y over r, the y-coordinate over the distance from the origin. So for angle A, it's going to be y over r. Whereas for angle minus A, the y-coordinate of the point on the terminal side is minus y. The distance of the point on the terminal side from the origin is r as well, because these two triangles are congruent. So we have minus y over r. Okay, what we do is we take the distance, the y-coordinate of the point on the terminal side divided by the distance from the origin. The distance from the origin in both cases are the same. The only thing that changes, one of the points has y-coordinate plus y, and the other has y-coordinate minus y. Looking at this, we see that the sine of minus a is minus y over r, which is minus, but y over r is the sine of a. That the sine of minus a is minus the sine of a. The sine of minus a is minus y over r minus y over r. Y over r is just sine of a, so it's minus the sine of a. So we have that the sine of minus a here is minus the sine of a. Okay, let's also look at the cosine relationship. The cosine function for minus a and for a. Since the cosine of an angle, if we go over here to the definition, is defined to be the x-coordinate of the point on the terminal side divided by the distance of that point from the origin. And if we look at these 2 points on the terminal side of the angle, P and P prime, they have the same x-coordinate, and their distance from the origin is the same. The cosine of minus a must be x over r, as must also be the cosine of a. The cosine of minus a and the cosine of a, since it involves the x-coordinate of the point and the distance from the origin, are the same. Whereas the sine of minus a was minus the sine of a, the cosine of minus a is exactly equal to the cosine of a. The cosine of minus a equals the cosine of a. So the only difference, the x-coordinates are the same, r is the same, the y-coordinates are the different ones, so therefore the sine which involves the y-coordinates is negative. Sine of minus a is minus the sine of a, but the cosine of minus a is exactly equal to the cosine of a. And although I drew my picture in with the angles in the first and the fourth quadrant, it would also be true if you had, say, an angle in the second and the negative is in the third. Okay. For example, if you wanted to find the sine of minus 20 degrees, it would be minus the sine of 20 degrees. But the cosine of minus 20 degrees would be exactly the same as the cosine of 20 degrees. We'll be using these facts a little later on. By the way, we only need to work them out for sine and cosine. Remember, all the other trig functions can be found if you know sine and cosine. For example, tangent is sine over cosine. That was one of the quotient relations. And cotangent is cosine over sine. Secant is 1 over cosine. Cosecant is 1 over sine, and so on. So if you know sine and cosine, you pretty much know everything you need for all the trig functions. If, for example, you needed to figure out the tangent of minus a, and you remember that tangent is sine over cosine, always of the same angle, of course. I may say tangent is sine over cosine, but I mean tangent of minus a is sine of minus a over cosine of minus a. Whatever the angle is here, it's the same in all of them. And we know that the sine of minus a is minus the sine of a, but the cosine of minus a is simply the cosine of a. We get minus sine a over cosine a, which of course is tan a. So the tangent of minus a is minus the tangent of a. And in such a way, you could get negative angle formulas for all of the trig functions. If you'll recall in the last tape, I mentioned that the definitions that I gave you for the trig functions were consistent with the earlier definitions that you may have had, the so-called SOHCAHTOA definitions, that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. These are for angles in a right triangle. Okay, to see that, what you do is consider a first quadrant angle. Pick a point on the terminal side, x comma y. R represents the distance from the origin. This is, say, angle A. We drop a perpendicular, and in doing so, we can think of this as an angle in a right triangle. Okay, x is this length, y is this. So we see that sine of A, which is y over r, is really opposite over hypotenuse. Cosine x over r, adjacent over hypotenuse. Tangent, which was y over x, is opposite over adjacent. Okay, bearing that in mind, we can get certain relationships for the angles in a right triangle. Let's say I have a right triangle. And let me label the angles A, B, and C, where the right angle is C. And very often the side opposite an angle, okay, its length is represented by the corresponding lowercase letter. So the side BC, the length of BC, where BC is the side opposite angle A, is denoted by a lowercase a. And the length of AC, which is the side opposite angle B, is denoted by a lowercase b. And the hypotenuse, the side opposite angle C, or opposite the right angle, is denoted by a lowercase c. Okay. Now, the sine of angle A is, of course, opposite over hypotenuse. That is the length of the side opposite angle A, which is little a, over the length of the hypotenuse. And the cosine of angle A, which is adjacent over hypotenuse, the side adjacent to angle A has length B, the hypotenuse has length C. Let us also write down the corresponding trig functions for angle B. Sine of angle B and cosine of angle B. Well, remember, here is angle B. Still, sine is opposite over hypotenuse. Opposite would be B over C. Opposite over hypotenuse, B over C. For cosine of B, adjacent over hypotenuse, A over C. And we notice that the sine of angle A is equal to the cosine of angle B, and the cosine of angle A is equal to the sine of angle B. Furthermore, because we have a right triangle here, when we know the sum of the angles in any triangle add up to 180 degrees, and since angle C must be 90 degrees, that leaves 90 degrees to be split between angles A and angle B. Angles A and B. Angles A and B are called complementary angles. That is, angles which sum to 90 degrees. Angle A plus angle B, they sum to 90 degrees. By the way, you could also write angle A plus angle B. If they're measured in radians, they sum to pi over 2 radians. In the first tape of trigonometry, you'll remember that we discussed two different ways of measuring angles, one in degrees and one in radians. And to transfer between, if you wanted to go from the degree measure to the radian measure, you would multiply by pi over 180 degrees. That's how we get the pi over 2 radians, equivalent to a 90-degree angle. Okay. Well, if this is true, let's see what we can write down. we have that the sine of angle A is equal to the cosine of angle B. That is, the sine of an angle is equal to the cosine of its complement. You see, if A plus B is 90 degrees, that means B is 90 degrees minus A, or B is pi over 2 minus A. It doesn't really matter at this point which one you use, but if you do go on to study calculus, you'll find that you will have to use radian measure in your calculus courses. So because of this, let me use this for the time being. But it means the same thing. Angle B is pi over 2 minus angle A. Okay. Now we have the sine of angle A is equal to the cosine of angle B. And furthermore, the cosine of angle A is equal to the sine of angle B. But we can write B as pi over 2 minus A, giving us the sine of an angle is equal to the cosine of its complement. And similarly, here the cosine of A is equal to the sine of B, but B is once again pi over 2 minus A. So the cosine of A is the sine of pi over 2 minus A, or the cosine of an angle is equal to the sine of its complement. So, for example, the sine of 20 degrees is equal to the cosine of 70 degrees, if you're using the degree measure, or the sine of, say, pi over 3. Pi over 3 multiplying by 180 degrees over pi corresponds to a 60-degree angle. Okay, the sine of 60 degrees would be equal to the cosine of 30 degrees, so I could write cosine of pi over 6, which is a 30-degree angle. Okay, maybe it would be helpful for you if I used that as an example over it. The sine of 60 degrees is the cosine of 30. The sine of an angle is equal to the cosine of its complement. If we have